So this is today is the fourth lecture of the thing. We have done two lectures on the motivation and one lecture on the definition of probability. Statistical regularity. So to explain statistical regularity, we have come to axiomatic definition. We have also checked the classical definition and which did not serve our purpose. So reasons to study probability: to explain statistical regularity happening in nature, a computer simulation of which is given in this one. I will be uploading this PDF, uploading the link to this PDF in the description of the YouTube video. So you can get over there, and if you click this here on this one, you will you'll be taken to this website which is designed by Dr. Arnab Chakraborty, and whose book we are going to treat as the textbook for this course. To use statistical, so that is the first reason to study probability. The second is to use statistical regularity in the field of economics, and to use the related concepts in other fields of sciences, like James Clerk Maxwell did in this paper. So as I showed you in the other video, Dr. Arnab Chakraborty talked about James Maxwell finding the velocity of the probability distribution of velocity of a bunch of molecule in a resting gas. So that thing you can find in this paper. So these are some very broad reasons to study probability. We have discussed this in detail in our first two classes. Okay, so now terminologies. We have seen these terminologies in the last classes as well. Experiment, a chain of actions which can be repeated. Random experiment, an experiment whose result is not known beforehand. Outcome, every possible result of an random experiment is called an outcome. Examples, two examples of experiments are throwing a die and mixing hydrogen and oxygen under electric spark. In case of the throwing a die, the outcome is not known beforehand, so it is a random experiment. On the other hand, the second experiment is a deterministic one, because we know it will always produce water. The outcomes of the experiment of throwing a die, that is a random experiment, are 1, 2, 3, 4, 5, and 6. We have all seen these things. Okay, sample space also we have seen, given the collection of all outcomes to the sample space. What we have not seen is the definition of event space the other day. This is something I missed. So event space is, let a random experiment have the sample space omega. We will be usually denoting the sample space by capital omega. Let a random experiment have the sample space omega. Then a collection script f of subsets of omega is called an event space of the random experiment if the entire omega is there in f. For every subset A in F, a complement must also belong to F, the family. F is there because it stands for family. It abbreviates the family, the word family. For any countable collection of subsets, their union will also be there in that family as well. As we talked about the other day, that we cannot consider every possible subset of the sample space as an event, and in that case we trip into Banach-Tarski paradox, some really completely counterintuitive and impossible theorems, impossible results in the real world of non-measurable spaces. So non-measurable sets, not spaces, non-measurable sets. So we need to filter our set of all events, set of all subsets for which we call events. So this is something. So it is a very, very tempting to announce at the very first look that this F, the collection of subsets of omega, should be power set of omega, but that is not the case. Power set of omega will contain those unnecessarily stupid sets over there. So that we need to have a filter in the power set of omega. So after that filtering, we get this filtered family which satisfies this thing, that omega is definitely there for every omega is there, and 1 and 2 together means phi is also there, a null set is also there. So a complement means omega minus a. Okay, A is a subset of omega. For all A in the family, A complement is also there in family. A complement is omega minus A. For any countable collection of subsets, A1, A2, up to, a countable collection, any countable collection, finite or infinite, their union must also belong to the family as well. So this family is called an event space. This is a subset or equal to power set of omega. This F family is a subset or equal to power set of omega. In case when omega is a finite set, we do not have any problem considering F as the complete power set of omega. Okay, so then this F actually equals to the any event, and that which comes from the classical definition of the probability. Classical definition of probability deals with finite sample space. So for finite sample space, we will not have any problem because in finite sample spaces the non-measurable sets do not occur. So we can always take for if omega is finite, F is equal to power set of omega. Fine. Some remarks. Members of the event space F are called events. That means the subsets of omega, they are called events. The above conditions together imply that for any countable collection of events, their intersection also belongs to F. This one, 2 and 3 together. 2 and 3 together. So this one, A1, A2, this collection belongs to F. So A1, A2, all of them belongs to F. This means A1 complement, A2 complement, all of them belong to F. That means union of all of them belong to F. That means intersection of all of them, whole complement belongs to F. Then again, the complement of the complement, that is the intersection of all of them, belongs to F. So as simple as that, the above conditions together imply that for any countable collection of events, A1, A2 up to any countable collection, their intersection also belongs to the family as well. For an event A in F, we call that A has occurred if any element small a in A occurs as the outcome of the random experiment. For an event A in F, we call that A has occurred, the event A has occurred if any element small a in A occurs as the outcome of the random experiment. If any element of there inside the event occurs as the outcome of the random experiment, we said the entire event has occurred, and these elements are called outcomes favorable to that event A. These outcomes are called outcomes favorable to this event A. Okay. Next, additions of probability. We have already seen this. Omega is a non-empty set called the sample space, and if be the set of all event space, then a function P is called a probability function if satisfies the following conditions. Number 1, probability is always non-negative. Number 2, probability of the entire set is 1. Number 3, the countable countable additivity. Countable additivity, am I saying the right word? I guess so. It is countable additivity. Yeah, countable additivity, countable sub additivity. Countable additivity this is. So for any countable collection of pairwise disjoint set, this countable additivity must be true. Probability of their unions will be sum of their individual probabilities. Okay, so that this thing is must be true for any countable collection of pairwise disjoint events. This must be true. All right, this one. So All these things, all these axioms are extremely easy and comes from common sense only. We want a probability function to satisfy these things. Now, so only problem with the third one is that we are actually assuming in case of finite collection, countable collection means countable or finite. For any countable collection, countable means countable or finite. It can be countable infinite or finite. So that together it is countable. So now this one, if it is finite, we have no problem to accept this one by common sense. Simple common sense says probability of one event and another event where they do not have anything in common must be the sum of the probabilities. Of course, there is no doubt about that. Of course, that common sense also extends to a countable infinitely many collection as well. There we are assuming something, that this union over here, this has a permanent destination. So there is a union of events, so there is a permanent destination. So this is sort of a, here permanent destination is sort of guaranteed. In a sense, understand this thing, that everything, all the ANs are subsets of omega. All the ANs are subsets of omega, and we are taking a union of them. So this, since we are taking union, this is an increasing sequence, like A1. My first term is over here is A1. My second term is A1 union A2. My third term is A1 union A2 union A3. So this is an increasing sequence. So every time we are actually adding more terms to that set, and this is an increasing sequence, but still bounded above, because definitely it cannot go beyond omega. Everything is inside coming from omega, so it cannot go beyond omega. So this thing, the convergence of, or the countable collection, countable union, countable infinite union of this collection is sort of guaranteed. There is no problem. Over here, this side is in this way, the thing is not very clearly seen. This one, probability of AN, this is a series, and the convergence of this series is assumed. So this is what these axioms actually say something. I mean, assume something more. This convergence is assumed, but judging from our common sense, this convergence should not be an issue. Okay, because I mean, the everything coming from the finite case, this probability should not go beyond 1. Okay, this is the entire probability. So this thing, this equal to sign means this is the entire probability. So in the right hand side, we have a series of non-negative real numbers, but this is a series, and this series is also bounded above by 1, because this is the total probability. P is there. So this also cannot exceed 1. So therefore, a series of non-negative real numbers, which is bounded above. So this has to be convergent. Fine. So this is equal to sign actually guarantees that if this has to equal to this one, then it has to be convergent. There is no other way out. Okay. Individually, right hand side may not be convergent, but when you assume that left hand side is equal to right hand side, then the right hand side has to be something smaller than or equal to 1. Then the convergence of the right hand side will be guaranteed, and this equal to sign is motivated from the finite case. Okay, so we have also discussed this thing in detail in the last class as well. Examples, yeah, this is what I had given you, and I have just retaken the things over here. So for any two events A and B, A subset B is implies probability A is less than or equal to probability B. I have done this one as I told the other day. For an event A from the sample space, probability of A complement will be 1 minus probability A. For any two events A and B, we have got this list over here. All these things will be true. For any three events, this is true. These are called inclusion exclusion principle. Okay, so this is included, this is excluded, this is again included. So this is called inclusion exclusion principle. This first three terms is inclusion. The next three terms is exclusion. What did I say? The first three terms is inclusion. The next three terms is exclusion. The last term is inclusion again. Like this one, probability A union B is probability A plus probability B minus probability A intersection B. The first two terms are inclusion. The last term is exclusion. So these are called inclusion exclusion principles. Fine. So all these things I had given you to try by yourself. Please try them by yourself using the axioms only and nothing else. That thing and set theory. Now this one I have done for you. For any n many events from a sample space omega, we have probability of their probability of their intersections is more than or equal to probability A1 plus probability A2 up to probability AN minus n minus 1. Now, something to understand here, that why this this proposition is something important, something tells you substantial, is because probability of intersections are always small things. Because when you are taking intersections, you are taking smaller and smaller events, so probabilities of them will be smaller and smaller. But this inequality says that this cannot be smaller than this. This cannot be smaller than this. So that this acts as a lower bound of intersection of events. So that is why it is important. Intersection is always very small. We do not it doesn't work if we know a lower bound of this one, that is always 0. But this works as a it doesn't help knowing an upper bound of this one. It is always 0. But if we can have a lower bound of this one, that knowledge is useful. Okay. It follows from here that this is true. Probability. This is called countable sub additivity. Here A1, A2 up to AN. Here we are not assuming that they are mutually exclusive, disjoint, pairwise disjoint. So here they do not simply add up with the individual probabilities do not simply add up, but this is less than or equal. So this is called countable sub additivity. Okay. The other one was countable additivity. Now we'll see the proof of this one. So we use induction on n. For n equal to 1, it is trivial. So we are proving the first one. So for n equal to 1, it is probability A1 is greater than or equal to probability A1 minus 1 minus 1, that is 0. So probability A1 greater than or equal to probability A1 equal to is there, so true. For n equal to 2, probability A1 intersection A2 is probability A1 plus A2 minus probability A1 intersection union A2. This is from the inclusion exclusion principle, what you are supposed to prove by yourself. This is greater than probability A1 plus probability A2 minus 1, because this part is always smaller than or equal to 1, and that comes from the axiom 1 and 2. So this is probability A1 plus probability A2 minus 2 minus 1. I have written this for this. So for n equal to 2, this is true. Assume the fact for n equal to k. Then for n equal to k plus 1, we have simple calculations, nothing special. So this thing, intersection of k plus 1 many things is equal to up to k, intersection up to k, intersection with k plus 1, and then I use the induction result for n equal to 2. So this is probability, this event, the first, this k many intersections plus probability of the last event minus 2 minus 1, and then again you use induction result for the n equal to k. So this is probability a1 plus a2. This is simple calculations, and this turns out to be true. So this is minus k, I guess. Yes, minus k. So this is k plus 1 minus 1. So it is true for this. Proves the first part. For the second part, apply the first part on the set of events a1 complement, a2 complement up to an complement, and apply De Morgan's law along with example 2. Example 2 is this one. Yeah, this is example 2. That probability a complement is 1 minus probability a. Okay, next, today we will do one fresh example. So this is we start with increasing sequence of events. Let a random experiment have the sample space omega and event space f. A sequence of events is called an increasing sequence of events if a1 is contained in a2, a2 is contained in a3, and so on. Okay, this is increasing sequence of events. Obvious definition, no surprises. Example. Understand the example carefully. For the random experiment of throwing a coin repeatedly, let the event an denote that there has been at least one head in first n tosses. Okay, so if a1 occurs, that is the first toss turns out to be head. A1 occurs means at least one head in first one toss. That means the first toss turns out to be head. Then A2 will definitely occur. What does A2 demand? A2 demands that there should be at least one head in first two tosses. So if A1 occurs, that means we have already got our head in the first toss, then A2 will definitely occur. That is, A1 is a subset of A2. If A1 occurs, then A2 will definitely occur. Similarly, if A2 occurs, then A3 will definitely occur. A2 is subset of A3 and so on. Okay, so this is increasing sequence of events. Next, decreasing sequence of events is exactly the other way around. B1 contained in B2 contained in B1 contains B2, B2 contains B3, B3 contains B4, and so on. Example, in the last example of the random experiment, consider the event Bn as there is no head in the first n tosses. No head in first n tosses. So if B1 occurs, that means there is no head in the first one. If B2 occurs, that means there is no head in the first two tosses. That means if B2 occurs, you can definitely say that B1 has occurred, because if there are no head in first two tosses, then there is no head in the first toss as well. If B9 occurs, that means if there is no head in first 9 tosses, then there were no head in first 1 toss, 2 toss, 3 toss, and 4 toss, up to all 8 tosses. So if B2 occurs, B1 definitely occurs, B3 occurs, B2 definitely occurs, and so on. So this is a decreasing sequence of events. Okay, so here this is blowing up, and here this is shrinking down. B1 is the biggest, then B2, then B3, and so on. Now, next monotone sequence of events, it is either increasing or decreasing. Then we have the following fact. Understand this. This is the original result what we are doing today. If n is a monotone sequence of events associated with a random experiment, then probability of limit of an is equal to limit of probability an. Probability of limit of an is equal to limit of the individual probabilities. Let us see a remark first. This proposition says that probability is a continuous function. Okay? This proposition says that probability is a continuous function. Now, yeah, let's see the proof, because I mean this is just the sequential definition of continuity. That is why it is a continuous function, and that in that sense. Okay. Let's see the proof. Case 1, increasing sequence. Case 2 will be decreasing sequence. Let A and B an increasing sequence and define. Now this one you must be very familiar about, that this is just like the keeping the same union but making them pairwise disjoint. This common trick, I guess both of you know, both of you are very much familiar with. You can unmute your mic and speak. Okay, Aditya. Okay, so this trick is very familiar, so no doubt about that. Next is Bn is a sequence of pairwise disjoint events, and also for each n, An, since it is an increasing event, increasing sequence, An is the biggest one. So An is actually the union of the first in many elements, because A1 is contained in A2, is contained in A3, contained in A4. So I mean, a union of A1, A2, A3, A4 will be the biggest one, A4 only. So An will be the union of first in many sets. And that union, finite union by our construction, is same as the B case up to from K first in many B case. Fine. So since An is an increasing sequence of events, limit n tending to infinity An, so it is blowing up. It is blowing up. So that means it is union of all the Ans. Union of all the Ans. This is the first equality is happening because An is a increasing sequence of events. That is same as n equal to 1 to infinity. An, I am replacing An by this quantity, k runs from 1 to n, bk. And this is nothing but, this is the definition of infinite sum, infinite union. I mean, anything infinite is defined in this way. Okay, k runs from 1 to n, and then n runs from 1 to infinity. That is how infinite sums or infinite operations are defined. So this is nothing but b runs n runs from 1 to infinity bn. So limit n tending to infinity An is same as union of all the Bns. Hence, probability of this thing, limit of An. So this is probability of this thing. So I'm applying probability on both sides. So this is probability this side and probability this side. So probability of limit of An, that is my left hand side, what we need to show, is equal to probability of this thing over here. This is equal to sum of, this is by countable additivity of the probability axioms. Bn's are all mutually disjoint, pairwise disjoint. So this is the countable additivity comes into play. So now this one is, I am just writing this infinite sum in the definition of infinite sum, limit n tending to infinity, k runs from 1 to n, probability bk. This is nothing but the definition of infinite series, nothing else. So this is n tending to infinity, k runs from 1 to n, probability bk is probability of union of k many bk's, because it is again countable additivity. Bk's are pairwise disjoint, so this is countable additivity. So this is this, and this one is an finally. From here, k runs from 1 to n, bk is basically my an. So this is limit an. So we have got my left hand side is equal to right hand side. Okay. So that is true for increasing sequence of events. Next we have decreasing sequence. Here we are going to use case 1. So call Bn as complement of An. Then Bn is an increasing sequence of events, because Bn, An is a decreasing sequence, so An complement will be increasing sequence. I would request you to do this yourself, to check, check this yourself, that this is actually true. Bn is an increasing sequence of events, and for every n, probability of Bn is equal to definitely 1 minus probability A. That is by the by our second example there in the list. Now, since An is a decreasing sequence, we have limit of An. I forgot to put n tending to infinity. Oh, fine. I have not put in limits of n anyway. Fine. So limit of An will be intersection of An, because A1 is the biggest, then A2 is contained in A1, A3 is contained in A2, A4 is contained in A3. So intersection of all of them will be the smallest one, the last one. So limit of An is intersection of all of them, is intersection of Bn complement, is complement of the union of Bn's, De Morgan's law. Hence, by case 1, probability of limit An is equal to probability of this part. This is 1 minus probability of this part. This is union of Bn. This is countable union of pairwise disjoint events. And not pairwise disjoint. Bn is simply the complement, so it need not be pairwise disjoint, but Bn is an increasing sequence. So probability of union Bn is limit of probability Bn, and that limit is 1 is a constant, so this is limit of 1 minus probability Bn. So 1 minus probability Bn is probability Bn complement, and this is probability A. So this proves the fact that probability is a continuous function.